Welcome to day 3 of our STL course. Today we will dive into one of the most widely used and powerful containers in C++, the vector. By the end of this session, you will not only understand how vectors work under the hood, but also you will be able to write clear, efficient code using them. Vectors are dynamic, versatile, and form the backbone of many real-world applications. Let's get started. Here's what we will cover today. First, we will understand what a vector really is, how it compares to arrays, and what makes it so powerful. Then we will explore how to declare and initialize vectors in various ways. We will follow that with vector insertion techniques, element access methods, and key behavioral insights about how vectors grow. Finally, we will solidify our understanding through a coding task and some practical challenges. Let's start with basics. A std::: vector is part of the standard template library and acts like a dynamic array. Unlike static arrays, vectors can grow or shrink in size dynamically. They store elements contiguously in memory, making them cache-friendly and fast for traversal. With built-in support for resizing, inserting, and accessing elements, vectors eliminate the pain of manual memory handling. This is why they are often a go-to choice for developers in both beginner and advanced projects. Vectors can be declared in multiple ways depending on what we need. We can start with an empty vector using vector int v. We can prefill a vector with default values using vector int v5 to create a vector of size 5 filled with 0. We can also provide an initial value like vector int v5,10, which gives us a vector of 5 tens, and with initializers list we can create and initialize in one go using curly braces. This flexibility is a huge advantage when working with different types of data or starting conditions. Inserting elements into a vector is done primarily using pushback, which appends elements at the end. It's very efficient, amortized constant time. For more control, insert lets us place elements at specific positions, though it's costlier as it might shift existing elements. Behind the scenes, when the vector runs out of allocated space, it doubles its capacity, reallocating memory and copying all elements to the new space. That's why frequent mid-vector insertions can be expensive. So always choose the right insertion method based on your use case. Accessing elements in a vector is intuitive. We can use the square bracket notation like vi for fast access, but it does not perform bounds checking. If we go out of range, it can crash our program. For safer access, we use v.addI, which throws an exception if the index is out of bounds. We also have v.front and v.back to quickly get the first and last elements. For robust and production-ready code, we prefer using @ unless performance is absolutely critical. This is a common area of confusion: size versus capacity. The size of a vector is how many elements it currently holds. The capacity is how much memory it has allocated, often more than the size, to allow for future insertions. When we keep adding elements and a vector exceeds its capacity, it allocates new memory using double and copies everything over. Understanding this is essential for writing efficient code. We can manage it using functions like reverse to pre-allocate space or shrink to fit to reduce memory usage. Let's walk through a simple program. We include vector to use the container and algorithm for sorting. We declare a vector with 3 elements, then use pushback to add another. Next, we sort the vector and print the elements using a range-based for loop. This snippet shows the real power of vectors: easy resizing, built-in algorithms, and clean syntax. If you are new to STL, this is your first taste of how expressive and concise C++ can be. Time for a mini challenge. Create a vector of even numbers from 22 to 220. Then insert a new value, say 999 at the second position using insert. Finally, print the entire vector using add instead of square brackets. This quick challenge will help you get comfortable with basic operations and ensure you understand the differences between access methods. Now it's your turn to build something a bit more substantial. Write a program that reads n numbers from the user into a vector. Once all values are collected, sort the vector in ascending order using sort. Then print the elements in reverse order. Bonus points if you handle edge cases like empty input or duplicate values. This task is designed to help you reinforce what you have learned so far: input, manipulation, and output using vectors. Let's take a step back and reflect. When would you choose a vector over a regular array? How do vectors compare in terms of safety and performance? What are the trade-offs when using insertions at various points? And finally, think of real-world applications. Vectors are perfect for undo history in editors, users' input tracking, and maintaining logs. Their versatility makes them invaluable. Here's your homework. Write a function to reverse a vector in place. No new vector allowed. Next, remove all even numbers from a vector using erase remove idiom. And for a bit of a stretch, try defining a vector of structs representing students with names and marks. Sort them by marks and print the top scorer. This blends vector concepts with custom data structures, just like you will do in real projects. To wrap up, vectors are a must-know in STL. They are dynamic, safe, and offer powerful functionality out of the box. Today we covered declaration, insertion, and access, all of which form the foundation for more advanced operations. In the next session, we will explore how to modify and manage vector more like a pro. Till then, keep practicing and experimenting. Happy coding!